All right, let us start the second lecture today. And the second lecture is dedicated to blockchain scalability. So what we will see in this lecture is basically we already know that blockchain has some scalability barriers. So what kind of techniques system designers are using to break those barriers? And I should also give the credit, this lecture was mostly prepared by a postdoc working with me. His name is Tiago Garrett. All right, so the limitations of blockchain scalability are well known. And so here you can see some collection of the news complaining about the pace of transactions in Bitcoin. Why hasn't my transaction confirmed yet? So what can we do about it? I'll be talking about 5 different techniques. So the first technique is there are some configuration that affect the scalability. The most prominent one, the most famous one is the block size. So the second technique is try to use more scalable protocols. How do we do more scalable protocols? In Bitcoin NG, which we'll see in the third lecture today, they're using microblocks instead of blocks. In Algorand and quite a few other cryptocurrencies, they're using committees. So instead of consensus being run by all the nodes, nodes select the committee representatives, and the consensus is only run by the representatives. The third technique is to use parallel structures instead of chains. So we'll have two lectures in this course on DAG-based systems. So where the blockchain is building not a chain of blocks, but a more complicated structure with parallel blocks and parallel transactions. So that allows some degree of parallelism without the need to basically to build all sequential chain out of all proposals. So that's another technique to improve the scalability. The fourth technique is building on top of a chain instead of changing the core of the protocol. So that's the idea of Lightning networks and off-chain transactions in Bitcoin, and that's the idea of what's called layer 2 in Ethereum. So this is what this lecture would be mostly about. And the fifth direction is that of sharding. So those are like the 5 main techniques used to overcome scalability barriers in blockchain. So I'm not going to talk much about number 2 and number 3 because we'll have dedicated lectures on that. But I'm going to cover 1, 4, and 5. So let's start from the block size. What's the deal with the block size? Why is the block size such debated topic in Bitcoin and in other cryptocurrencies? Because there is a clear trade-off. What happens if we make very long blocks? Well, there is a positive side, there is a negative side. The positive side is that we would be able to include more transactions in a single block. Therefore, in the best case, we should be able to increase the transaction rate, the transaction throughput. What's the downside? The downside is that longer blocks take longer to propagate. Like they are more prone to failure, so the rate of failures would increase a bit. And the longer propagation leads to higher risks of attacks. It may also lead to higher, and because of the longer propagation, we may also end up with a higher branching. So there is a trade-off. And there are always proponents and detractors, right? So in this context, I would like to mention SegWit and SegWit 2x. SegWit came out around 2013, if I'm not mistaken. It was a soft fork of Bitcoin with two components. After the block structure, two components, two ideas. The first idea was to alter the block structure so as to move the location of the signatures such that the signatures would not take time during the verification, or at least some of the operations would be performed faster. So it was an optimization about the block structure. But the more interesting was the second change, which was to allow block size to be more flexible based on block weights. So according to SegWit, each block may be assigned a different weight, and the higher the block weight, the longer the block is allowed, the maximum size of the block is allowed to be. So how do we decide on weights? Well, there are different components that affect the block weight. But ultimately, the most important part is that this resulted in longer blocks in practice and higher transaction throughput. And it was a soft fork, so again, like it was backward compatible. The newer system after the change was still being able to work with the old clients from before the change. So it's a soft fork. Therefore, it was accepted, and most Bitcoin clients today adopt SegWit. Now, in comparison, there was SegWit 2x, which was a hard fork, and it was more straightforward. Let's double the size of a block. So it was pushed by the miners, but it was mostly opposed by node operators and system designers. And it was highly controversial, so there was like debate for about a year, and at the end, it was abandoned. So this is one exemplification of what people do regarding the configuration of blockchain. Now the next technique, so that's obviously the simplest technique of them all. The next technique we are going to consider is building on top of a chain. So the idea is to create something outside the main chain. How do we do that? So two on-chain transactions, there would be one transaction put on the chain whose purpose would be to start a separate chain, let's call it a side chain, and there is a second transaction which would end the separate chain and transfer the results back to the main chain. So everything that occurs within the side chain is invisible to the general blockchain participants. Only the end result is recording due to the second transaction of the two. So why is it faster? Well, it's faster because we don't need to run consensus on the transactions. Imagine that a side chain would include 100 transactions. We don't need to include those transactions individually and run consensus on them. There might be small number of participants in a given side chain, maybe just 2 participants or 3 participants instead of all the large scale. Because it's created coordinatedly. Say 2 nodes decide, okay, now we are going to do a lot of trading between us, so let's do it separately from the main chain. In this case, they create a side chain. So it would be much faster for them, because now they don't need to push all those transactions. They don't need to pay the fees to the miner for each individual transaction. All they need is one big transaction at the end in order to flush it back to the main chain. So we'll talk about Lightning Network in Bitcoin, and we'll talk about tier 2, layer 2 in Ethereum. Lightning Network in Ethereum based on micropayment channels established between just two parties. And so the micropayment channel is created with a special transaction called a funding transaction, which locks fund on the main chain. So it takes fund from the main chain, UTXOs. It locks them, so now they are not usable on the main chain. And now, like there is a period during which transactions are done on the side chain, and at the end, those the funds from the side chain would be flushed back to the main chain, at which point the UTXOs may be unlocked or may be spent. And in case of misbehavior, so what happens if the two parties disagree while doing transactions on the off-chain, on the side chain? Well, it's more difficult, of course, compared to, so on Bitcoin we have no dispute. Everything is visible, right? On side chain we can have disputes. So disputes would take long time to resolve. Probably long. So in that case, the parties would probably lose in terms of the speed. I'm not talking about financially. I'm saying in terms of the speed of completing all transactions, the parties would lose if there is a dispute. But hopefully, most of the side chains would be resolved without disputes. So here's an illustration, right? So Bitcoin blockchain, Lightning Network, right? So there are two nodes, A and B. Say node A has balance of 5 Bitcoin, node and then, okay, then the node would send 2 Bitcoins to the Lightning Network. That's the starting transaction. And then we have, then we have, okay, it's a typo here. It should be node B with a different balance of 2 Bitcoins, which would send 1 Bitcoin to the Lightning Network. So now on the Lightning Network, this one starts with 2 Bitcoin, and this one starts with 1 Bitcoin. So then they do some transactions between them. Say, for example, node B would be receiving 0.5 Bitcoins from node A, and then later node B would send 1.5 Bitcoins to node A. And node B can also send some transactions outside of the channel. So in this case, there is transaction 3, which transfers funds, in which funds are transferred to node X. And then at the end, there would be the end transaction, in which the results for node A and the results for node B would be sent back to the main chain. So again, the advantages and the disadvantages. The advantage is the throughput and the latency are limited only by how fast the two parties can interact with each other. There are no fees to the miner. And there is another advantage. This scheme can also work cross-blockchain. So some of the bridges, last time I mentioned interoperability between different blockchains. So some of the bridges work based on such channels. Disadvantages. So we need to constantly see the main chain if the other party is trying to publish some premature settlement. So the two parties on the side chain do not trust each other. Okay, so they need to also watch what the other party is. So each party would need to watch what the other party is doing with respect to the main chain. Main chain, not channel. And the disputes can be resolved slowly. And opening a channel is subject to the latency of the main chain. So you do not want to create a side chain in order to do just a couple of transactions. You only want to do it if you want to perform a long sequence, a bulk of transactions. Ethereum, layer 2. So in Ethereum, layer 1 is the technology, is the blockchain technology itself, while layer 2 is what you build on top, right? In essence, it's the same principle as Lightning networks. So in layer 2 in Ethereum, we batch multiple transactions into a single one, sent to the main channel, main chain, sorry. And there are multiple layer 2 solutions. Those solutions differ by the trust model between the participants. They have different goals, and therefore they're suited for different applications. They use different consensus protocols, and so on. So let's take a brief, I'm not going to present everything, and by the way, layer 2 was introduced just a couple of years ago, so or 3 years ago, so it's still in development. So I'm only giving you some overview of of the things that exist in layer 2 scaling on Ethereum. So first, Ethereum has state channels, which are pretty much the same technology as Lightning networks in Bitcoin. However, it also has optimistic rollups, ZK rollups, zero-knowledge rollups, Validium chains, plasma chains, and side chains. So they all serve the same purpose, but they have slightly different solutions and models. So what is optimistic rollups? The idea behind optimistic rollups is to perform computation off-chain, publish results on the main chain, and then bundle hundreds of transactions in a single transaction. So far, it's the same as side channel. The main difference is that no proof is provided. The main difference, when you publish the final results of the side chain on the main channel, on the main chain, so the question is, what exactly do you publish at this point? How much of the history of what happened on the side chain do you publish? How stringent the proof from the side chain need to be? How much privacy do you want to preserve with respect to what happened on the side chain? So these are some of the differences between the solutions. So in optimistic rollups, there are no proofs. In that sense, they are optimistic. They hope that lack of proofs would not cause any problems. So optimistic rollups, the main idea is that it saves computation costs, right? Because the computation, the main point in optimistic rollups is that all the computation, transaction in Ethereum is not transaction in Bitcoin, in the sense that they can be like programs. They can perform some, maybe not very heavy, but at least non-trivial computation. So there is significant cost of performing computation on the main chain, main net of Ethereum. And the main motivation for optimistic rollups is to move the computation. So it's not the fees, it's not the same as, the motivation is different from motivation in Bitcoin. We want to move the computation to offload the main net of Ethereum. So optimistic rollups save computation costs, but doesn't improve the latency a lot. Next we have zero-knowledge rollups, in which we bundle hundreds of transactions into a single proof, and we provide a zero-knowledge proof without disclosing the details of transactions. So we provide proofs without disclosing the details, zero knowledge. Side chains is a reserved term can be confusing because sidechain is just a concept, right? But in Ethereum, sidechain is a reserved term. It's for specific types of layer 2. What type? So sidechain in Ethereum is essentially a different ledger with its own consensus algorithm, everything, its own storage, everything. So, in the middle of running on mainnet, you decide to start your own ledger, right? And you do everything on a different ledger, proprietary ledger, probably smaller number of participants, maybe more scalable consensus. And then at the end, you decide to flush the result back to mainnet. And plasma chain is something in between. So it uses the idea of optimistic rollup, so perform computation off-chain. It also has its own chain, but it's not a full-fledged ledger, unlike side chains. So here's an illustration. It's called Matisse, a Matic side chain. Yeah, sorry for the quality of the picture. It's not really visible. So anyway, this is the mainnet of Ethereum, and the mainnet can be divided into different points, into different checkpoints. So there is a checkpointing between the main chain of Ethereum and the side chain. That's the idea, the checkpointing. They synchronize about the result periodically, or there are certain triggers for synchronization between the main chain and the side chain. Okay, so this is what I wanted to say about layer 2. Now the next technique is sharding. What is sharding? Sharding is layer 1 solution. So we are changing the fundamental technology of blockchain. We are not building on top of it. What's the idea? Nodes are split so in separate shard. Shard is a fancy name for partition. So nodes are split into different partitions, and each shard maintains a separate blockchain. And the transaction, so everything is split between the shards. The nodes, the storage, and the transactions. So, for example, how do we split? For example, we decide that Dr. Moody would be on shard 1, while I'll be on shard 2. So all my data would be on shard 2, while all Dr. Moody's data would be on shard 1. So, and then if most of the transactions would be within the same shard, so we need to be smart about how we divide, right? We want most of the transactions to be within the same shard, but some of the transactions can be cross-shard, and we need to have provision for that. So here's an illustration, 2 shards, and we can even have branches within each shard, right? Because it's like a separate blockchain. And then we can have a cross-shard transaction. Cross-shard transaction would be like me transferring some funds to Dr. Moody. This transaction would need to result in subtracting my balance and adding to the balance of Dr. Moody, right? So it affects the state of both shards. Cross-shard transactions are much more expensive to implement in a sharding system compared to intra-shard transactions within the same shard. So why is it a good idea to use sharding? Sharding is a popular technique, not just in blockchains, but in general, in a replicated system. So it helps with scalability. First and foremost, we split the nodes. So the consensus needs to be run only on a per shard basis. only between the nodes of that shard. And the smaller the number of nodes, the faster it is, and the more robust. It also helps, of course, that we split the storage, right? So now there are some nodes which only store my data, and some other nodes which store the data of Dr. Moody. So per node, it's less data to store. So it also saves on the storage cost, though usually it's the consensus cost. It also helps with the computation, right? Because as mentioned, transactions in Ethereum and another system can be reasonably computationally extensive or intensive. Therefore, it's good that not every node needs to execute every transaction. So that's the idea of, the benefits of sharding. However, unfortunately, sharding lowers security. Imagine that you use sharding on Bitcoin, just for the sake of illustration. There is no sharding on Bitcoin, but imagine that there is, because it's the same principle as sharding on many other systems. So in Bitcoin, in order to successfully launch a double spending attack, which we discussed, the attacker needs 51% of the total mining power in the network. In the shards, okay, so this is what you see on the left-hand side. On the right-hand side, on the other hand, imagine that there are 10 shards. In this case, the attacker only needs instead of 0.51, the attacker needs only 0.051 fraction of the total mining power in the network, because it's much cheaper to overcome the mining power of a shard compared to the entire system. Another problem is with Byzantine nodes. We said that, so we know that Byzantine consensus cannot be reached if more than 2/3 of the nodes are honest. So if you have too many Byzantine problems, it's a problem. Too many Byzantine nodes, it's a problem. Now, when we divide the nodes across shards, we may be unlucky. We may decide to put all Byzantine nodes in the same shard. And then they would do much more damage there compared to the entire system. So that's another problem with sharding. So let's take a look at one sharding system in the context of blockchain. It's called monoxide. In the system, the shards are just called zone, and there is a number of zones, which is a power of 2. The system includes efficient cross-zone transactions, which they call relay transactions. Nodes are split based on their ID they use to mine blocks. So in this case, it's like one of the most of the simplest, but also most typical technique to decide on the shard to which the node belongs is just to randomly to use some hashing on the ID of the node, right? And produce some number, and essentially it's like random assignment. One interesting idea of monoxide is they use the Chukunu mining. Chukunu is the word for arabesque in Chinese. So the idea of mining power of crossbow, mining power of each zone is similar to the whole network. Okay, we are going to talk about Chukunu mining in a bit. And there is also concern about how to do communication between the shards effectively. So they use distributed hash tables for fewer discovery, and they use some swarm protocols. Let's take a look at the relay transactions in monoxide. Imagine that there is a transaction which transfers some funds from the user in zone A to the user in zone B. Okay? So what monoxide does, it splits such a cross-shard transaction into two transactions. One transaction would be to withdraw funds from the user in zone A, and the second transaction would be to deposit funds in the user account in zone B. Now the point monoxide is making is that the deposit can be delayed. So the withdrawal needs to be immediate to make sure there is funds, but the deposit can be delayed a bit. So this is illustrated here, right? So the transaction relaying, right? So the deposit, the withdrawal is added to this block in zone A, this shard, while the deposit will happen in a later block in zone B. The latency is relative to the initial transaction, right? So obviously we don't want to delay it too much. Now there is an interesting complication that arises from branching, because each shard may have its own branching. So you see what happens here? What happens here is that initially there was a block A in zone A, and that block included a cross-shard transaction that transfer funds to zone B. So you see there is a relay transaction here. But later, a different branch overcomes this. However, while it happens, or before it happened, before block A became abandoned, what happened in zone B is that the relay transaction successfully went in, was confirmed, then later we had more blocks on top of it, and now we cannot easily cancel the deposit transaction. We cancel the withdrawal. We cannot cancel the deposit. So we need to compensate for that. And there's a special mechanism in monoxide to compensate for such a situation, which is a bit complicated, so I'm not giving the details. Instead, the point is to explain the typical problematics of using sharding in such systems. Chukuno mining. So in Chukuno mining, a miner can use a single POW solution to create multiple blocks at different zones simultaneously. So that's an interesting concept, right? Because, okay, first of all, the idea to allow the same miner to create multiple blocks in different zones, right? Because in monoxide, the partition between the nodes it doesn't need to be perfect, and the same miner can participate in more than a single zone, can participate in multiple zones, and can contribute blocks in multiple zones, but maybe not all zones, a subset of zones. Multiple, plural, but not all. And in this case, a single crypto puzzle allows the miner to produce multiple blocks, but not more than one block per zone. And the difficulty is the same in each zone. So we need to adjust the difficulty like in Bitcoin, but we have to make sure that the difficulty stays the same across different zones. And there are also security guarantees which rely on all miners employing this strategy. So there is quite an interesting proof of security guarantees due to using Chukuno mining. So again, this is just a very high-level illustration of the typical techniques used in sharded blockchain systems. And this is the end of the second lecture today.